Okay, so we will continue from where we stopped and continue with half-life. So previously is alpha decay, beta decay, gamma decay. So we will continue with half-life. Okay, so what is half-life? What is half-life? Half-life is the symbol of T. Okay, with the symbol of T. This capital T represents period and a small half 1 over 2. Okay. T represents period, so half period is a time taken for a sample of radioactive nuclei to decay to half its initial number. Okay, that is what it is. After an unstable radioactive nucleus decay, the new nucleus that is formed may also be unstable. It will experience a series of continuous decay until a stable nucleus is formed. So, for example, here we have uranium-238 undergo alpha decay. Okay, this represents alpha decay. So the time it takes is 4.5 times 10 power by 9 years. So this is 4.5 billion years. Half of the uranium-238 will decay and become thorium-234. Okay? So this is the half-life of uranium-238. Okay? That means it takes the time of 4.5 times 10 power by 9 years for all of the uranium-238 to decay by half. Get the idea? Okay. So that is the half-life of uranium-238. And then thorium. Thorium after 24.1 days of thorium-234, again the isotope of thorium-234. After 24.1 days, thorium that undergo beta decay will decay by half. That means half of the thorium-234 will decay into, I think this is palladium, okay, 234, okay? You understand? Okay? So, and then this palladium, after 1.8 minutes, half of the palladium will decay, undergo beta decay into uranium-234. Okay? So you see this uranium and this uranium, they are not the same uranium. See, the isotope is different. Okay, this is 234, this is 238. So they are a different isotope of uranium. Alright. So 1.8 minutes is the half-life of palladium 234. 24.1 days is the half-life of thorium 234. 4.5 billion years is the half-life of uranium 238. So, because after decay, okay, after undergoing radioactive decay, this thorium-234 is still unstable. Okay, not yet stable. It is more stable, but it is not yet stable. Okay, understand? After uranium-238, decay becomes thorium-234. This thorium-234 is more stable than uranium-238. But thorium-234 is still unstable. So it will continue to undergo radioactive decay, palladium-234. And then this palladium-234 also more stable, but not yet stable. So undergo radioactive decay, uranium-234. Not yet stable, undergo radioactive decay again, become thorium-230. Okay, 230. Okay, this thorium and this thorium are two different isotopes of thorium. Okay, undergo this solid 230, undergo radioactive decay, again become it is the this two is there's something wrong with the typing there. Okay, same symbol, but the proton number is disappear and then check. Okay, so this is radium, radiated radium. Radiated radium. Atomic number 88. Atomic number 86. This is correct. Okay, this one is correct. This is supposed to be the radium. Okay, so this is wrong. This is supposed to be Rn. Okay, radium. Okay, so I think mistake here. All right, so this radium undergo radioactive decay become radium. Okay, and then this radium undergo radioactive decay become polonium, polonium become plumber or lead, then bismuth, polonium, plumber, lead and lead, bismuth, polonium, lead. Okay, so at the end, when it becomes lead 206, then this is stable. So lead 206 are stable. And then when it becomes stable, that means when it becomes lead 206, then it will stop to undergo radioactive decay. So that means this lead 206, it is not radioactive. Not radioactive. It will not release radioactive radiation. Okay, it will not release radiation. But all the rest from here, uranium until the polonium here, it will undergo radioactive decay. So it will release radioactive radiation. So depend on what kind of radioactive decay that it undergo, then it will release different radioactive radiation. So for example, if it undergo alpha decay, then it will emit alpha particle. If undergo beta decay, then it will emit beta particle. If undergo gamma decay, then it will emit gamma ray. Okay, okay, so this is half-life. Remember, half-life is the time taken for sample of radioactive nuclide to decay to half of this initial number. Okay, if you not quite sure, not understand, so let's say like these are half-life. Right? Okay, so for example, you have 1, 2, 3, 4, 5. Okay, you have 20 unstable nucleus of bismuth, for example. Okay, so after 5 days, this bismuth half of them will decay. That means maybe this one, this one. Okay, in the 5 days, decay. Okay, for example, these will decay and become colonial. That means this one, this is no longer this one, but become colonial 210. Okay, this one is still 210. Okay, you understand? So these 5 days is the half-life of the this one 210. Okay, get that idea. So this is what it means by half-life. Okay, it's very simple. Okay, continue. Okay, so uranium-238 is a radioactive element with a long half-life. That is about 5,000 million years. That is 5 billion years. So just now we got see that it is actually like 4.5 billion years. Okay, or 4,500 million years. Okay, so this element is trapped during the formation of rocks. The trapped uranium-238 will decay and eventually form a stable Lab-206, as shown in figure 6.6. So this decay process takes a long time because the decay rate is low. Decay rate is low, that means decay very slowly. Okay, it decay very, very slowly. So you can imagine uranium-238, the time for it, the half-life is 500 million years or 4.5 billion years. So that means if you have, let's say 10, if you have 10 atoms of uranium-238 that have unstable nucleus, okay, so you have to wait 5,000 million years, then only 5 of the uranium will decay. So that means the decay rate is very low. That means very, very slow. Okay, decay very, very slowly. Okay, takes the idea. Get the idea. Okay, so by determining the ratio of Lab-206 to uranium-238 in the rock sample, the age of the rock can be estimated. Okay, the higher the ratio, the older the rock. This geological method of measurement can also estimate the age of our Earth. So, do you know the age of our Earth? So, the age of our Earth, for your information, is about 4.5 billion years. So, that means from the day of formation of our planet Earth until now, the uranium-238 only undergo one half-life, and only undergone one half-life only. Okay? All right. So, we understand. So, because we know the half-life of the radioactive substance, so if we know the half-life and we know that after it decay, it will turn into one element. Okay, it will turn into one element. So that means that if we take the ratio of the lead, which is the final product of the decay of uranium, and compare with the uranium lead and the ratio between lead and uranium, then we can estimate. Okay, the keyword here, estimated, that means agak-agak, okay, estimate. We will not be able to know exactly many years already. That means the rock is formed how many years ago. Okay, so a lot of the rocks are many of the rocks are formed during the formation of Earth. So that means if you know the age of the rock, that means you also can estimate the age of the Earth. For information, not all rocks are formed during Earth formation. Okay, there are rocks that are formed through other processes, okay, like volcanic rock and so on. They are formed after the lava, volcanic lava cool down, okay, and then rock. Okay, right. So you got learn all of that rock formation on one size. Right? Okay, so here are info gallery. Radioactive element material is usually stored in a thick sealed container made of lead for safety purposes. Okay, so lead, a thick lead can block the radiation from escaping. Okay, can block the radiation. Okay, you got learn this when you got learn about the penetrating power of different radioactive radiation in Form 3 also. Okay, you will learn about the different penetrating power. So alpha particle have low penetrating power. Beta particle have higher penetrating power, and then gamma ray have the strongest penetrating power. Okay, all of this you must you need to go back to Form 3 and take out the Form 3 science book and do the of that. Okay, because those are all the basic knowledge that you need. All right. So radioisotopes are isotopes with unstable nuclei that emit radioactive radiation. Okay, so as what you already learned in chemistry, one element have a lot of different isotopes. Okay, have a lot of different isotopes. So some isotopes are radioactive. That means are unstable, will decay and emit radiation. Some isotopes are stable. So those isotopes of an element that are unstable, we call them radioisotopes, because these isotopes will decay and emit radiation, radioactive radiation. So we call them radioisotopes. Yeah. So for example, here, okay, determining the age of granite rock. Okay, the granite rock contains uranium radioisotope. The uranium nucleus undergo radioactive decay to form a daughter nucleus lead. So after many years, some of the uranium turns to lead. So by determining the ratio, okay, by determining the ratio between how many uranium is left and how many lead is there, then we can determine the age of the rock, right? Then we can know how many years already passed. Okay? Alright. So next, we determine the half-life of a radioactive substance from its decay curve. Alright, so we want to learn about the decay curve. Okay, so we are not going to discuss here this experiment. So this activity. So basically, this activity is to show us how do the radioactive decay works, okay, or how do the half-life works. Because half-life, we learned that half-life is the because we learned that half-life is the time taken for half of the radioactive substance. Okay. So for example, so for example, here we have plastic bag containing 60 dyes per bag. 10 plastic bag, every plastic bag for 60 dyes. Okay, so divide the class into 10 groups. Each group provided with plastic bag containing 60 pieces of dyes. So throw the 60 dyes on top of the table. Remove all dyes which display the number 3 and record the number of dyes left. Okay, and then throw the remaining dice again on the table and put the die and display the number 3, and got the number of dice left. So we did repeat step 4 for 20 times. Okay, repeat step 4 for 20 times. Right? Alright. So we record the result. Okay. So see here, the explanation here says in activity 6.3, each dice represents one radioactive nucleus. The dice display the number 3 represent a decay nucleus. The remaining dice are considered as nuclei that have not decayed. The number of dice that display the number 3 represent the activity of the radioactive sample. So your class result will not change if the activity is repeated with the dice displaying the number 1. Okay, for a throw, because the probability for all numbers is the same. Okay, so the activity of a radioactive sample is directly proportional to the number of radioactive nuclei present in the sample at the time. So the activity of a radioactive sample is the number of decay per second, namely the number of radioactive particles emitted per second. So that means every 1 second it emits how many radioactive particles. Okay, but we are going to discuss that later. Okay, but we want to talk about this dice throwing. Yes. So for example, when you throw the dice, okay, there is 1/6 chance for the dice to display the number 3. Okay, got 1/6 chance, right? So the dice got 6 faces. So the chances for number 3 to come out is 1/6. So that means every time you throw the dice, okay, every time you throw the dice, you will find that about 1/6 of the dice will show roughly about 1/6 of the dice will display to show the number 3. Okay, so because you have 60 dice, so when you throw the 60 dice, so roughly you will find 10 dice that show number 3. About roughly 10 dice that will show number 3. Right now, this is very logical, right? According to probability. Okay, the dice got 6 faces. 1, 2, 3, 4, 5, 6 number. So when you throw the dice, each of the dice has 1/6 chance to show each number. That means each number has the probability of 1/6. Right? So if you throw 60 dice, that means roughly, it will not exactly lah, but maybe 8 dice, maybe 9, maybe 10, maybe 11, maybe 12 dice to show number 3. Okay, so you take away the number 3, and then you will left about 50 dice. Okay, you left about 50 dice. And then you throw again, and then out of the 50 dice, 1/6 will show number 3. Okay. Then you take away, and then so the number of dice will get less and less. You get that idea? Okay. So so when we Okay, so repeat step 4 for 20 times. So that means you have to repeat the same thing for 50 times. Okay, for 50 times. So I think this activity does not actually like represent the actual half-life, because it goes by the number 3 only. Actually, it would be better if it says that if it show number 4, 5, or 6, then you take away the times. Okay, show number 4, 5, 6, because so that it shows that after one half life, about half of them are over. Okay. Okay. So anyway, the result that you get, you will be able to see that the number of dice left will get less and less and less. So after a number of times, okay, you will be able to see that the graph. From the graph, you will be able to get a graph that roughly look like. Okay, be able to get a graph that roughly look like this. Okay. Okay, because every equal number of time, okay, the number of dice will decrease by half. Okay, after the same number of time, it will decrease by half. So you will get a graph that looks like this. So this is number of dice. So if so to find the half-life, of the dice, to find how much time. So for example, 60 dice. So you throw, you will get less and less. So you find okay, when 60 dice change into 30 dice, what is the time? Okay, this time is how long? Okay, get the idea. How long does it take for the dice? 60 dice to reduce until 30 dice. And then how long does it take for 30 dice to reduce until become 15 dice? Okay, we will find that this time is roughly the same. So for example, this time is let's say 5 minutes. Okay, 5. Let's say this time is 5 minutes. So this time will be about 10 minutes. Okay, and then reduced by half, it will be about 7, okay, 7 or 8 dice. And then you will find that the time is this time is about 15 minutes. So that means every equal amount of time, 5 minutes, 10 minutes, 15 minutes, we will be able to see that the number of dice increased by half, by half, by half, by half. Okay? So every time we throw the dice, and it shows number 3. So the number 3 represents the dice that already the radioactive that already decayed and everything out. Decay already, that means change to other kind of activity, so that pick up. So the one that is left is still unstable. So we throw the dice that is left. Okay, we throw many times. So this the number 3 represents the number of radioisotope that decay in the same amount of time. Okay, after the same amount of time, how many? Same amount of time, how many? Okay, so So one way that we can do this activity even better is actually we should put in the time. Okay, time. That means you throw the dice in the same amount of time. That means you throw the dice, you count number 3, how many, take out, and then the time that you do this activity should be restricted. For example, let's say, okay, you have a time of 2 minutes. Okay, 2 minutes to do all of this. Okay, so for example, the first time you throw, you got 10 dice that show number 3. So you have to throw the dice, find all the number 3, take out how many number 3, or you count how many dice are left. All of that you must do in 2 minutes. And then after that, you throw again, and then you must do everything in 2 minutes. So every 2 minutes, you throw one time. Every 2 minutes, you throw one time, throw one time, throw one time. So we can get a better better idea of the actual situation of the video. Alright? So I hope that you can understand. Okay? Okay, so you see here. Okay, so we want to look at here. It says that activity of a radioactive sample is directly proportional to number of radioactive nuclei present in the sample. Okay, so we want to know what does it mean by activity of a radioactive sample. Okay, activity of a radioactive sample is the number of decay per second. Okay, number of decay per second. That means every 1 second, how many unstable nucleus decay. That is what we call activity of radioactive sample. So, okay, or essentially, namely the number of radioactive particle emitted per second. So that means every 1 second got how many radioactive particles are emitted. So for example, if every 1 second got 1 radioactive or 1 unstable nucleus decay, then that means every 1 second got 1 radioactive particle emitted lah, right? Okay, for example, okay, for example, like this. Okay, so let's say that after 1 second, got 2 unstable nucleus that decay. So every time this decay, it will emit 1 radioactive particle. So for example, alpha particle. Okay, this one alpha particle come out. So that means every 1 second got 2. Every 1 second got 2 radioactive nucleus that decay, and this will also mean that every 1 second got 2 radioactive particles that are emitted. Again, 2 alpha particles shoot out. Get that idea? So this is the activity of the so this is what we call the activity of the radioactive substance. Okay, if there's more, for example, in 1 second you can emit 5, can emit 10, 1,000 radioactive radiation. That means radiation that in 1 second. And the number of radiation that can be produced depend on how many unstable nucleus. If you have more number of unstable nucleus, that means in the same amount of time, you have more. That means you have more radiation than okay. So for example, if this number of, for example, here is got 20 unstable nucleus. If we double, that means 40. So every 20 in 1 second can be 2 decay. So in 20, this 20 also every 1 second will have 2 alpha particle come out. So that means if the number of unstable nucleus is more, then the activity will be higher. Okay, get the idea. So that's why it says that activity of radioactive sample is directly proportional to number of radioactive nuclei present in the sample. Okay, get the idea. It depends on the number of radioactive nuclei present in the sample. So usually the half-life do not affect this very much. Okay, do not affect this very much. So it depends on the number of radioactive. So if there are more, if the number of radioactive nuclei is a lot, okay, of the same substance with the same half-life, then the activity can be higher. Okay. All right. Okay, I hope you can understand what is the activity of radioactive sample and how is it that the activity is directly proportional with the number of radioactive nuclei. All right. Okay, so the concept of half-life can also be expressed in the form of a decay series as follows. So you look at this. So this N0 is the initial number of radioactive nuclei. And then after one half-life, this number will increase by half. Because half-life is a time taken for the radioactive nuclei to increase by half. Okay, or half of the decay. So the number will increase by half. So after one half-life, increase by half. After another half-life, increase by half again. So that means we have divide by 4. After one half-life, divide by 2 again. So become over 8. And continue. So we can write, so we can say that after n half-life, okay, after n half-life, this original number of unstable nucleus to multiply with half powered by n, then you will get the number of, okay, you will get number of the unstable nucleus that is left. Okay, left how much? So number of radioactive nuclei that has not decayed equal to half powered by n times n0. Okay, so this is the number of radioactive nuclei that has not decayed after n number of times of half-life. Okay, after n half-life. Okay, get the idea. So this n is because it's a number of half-life, so it is limited to positive integer. That means it cannot be negative number of times because this is number of times that it happened. Okay, so it cannot be uh, negative, it cannot be half. Okay, or it happen half number, happen 2.2 number. Okay, happen one time, happen two times, happen three times, happen four times. Okay, like that. Okay, how many half life will be passed through? One half life passed through, two half life passed through, three half life passed through. Okay, get the idea. Okay, so we can show this is the example lah, huh? This is the example. So initial number, original number is n0. Okay, number of the unstable nucleus. So after one half life, so the number will decrease by half life, so times half. If after another half life, then times half again, so you have half power by 2 lah. So half 1/4 of the original number. 3 half life times half again. Okay, so half power by 3. So that is why you can say that after n number of times, so after n half life, we can say that the number of unstable nucleus that is left can be calculated with taking the original number times half power by n times the half-life already passed. Okay, get the idea. So that is why the number of unstable nucleus left is equal to half power by n times the original number. Okay, get the idea. Okay, so so this is the decay curve, the decay curve. So we can see that this example of decay curve. So after one half life, okay, this is after one half life. So the number of the unstable nucleus will decrease by half. Okay, after another half life, it will decrease here to here. Okay, here to here, decrease by half. Okay, decrease by half. After another half life, here to here, decrease by half again. So after every half life, so for example, here is 4. After 4 times half life, so this one will decrease by half. You see, okay. So if we compare the curve, we can see that which one, for example, if we compare the curve of different radioactive samples, then we can see which one has higher decay rate and which one has lower decay rate. So if you have higher decay rate, then you can see that the curve is steeper because the number will decrease very quickly. Right? With the number of the radioactive nuclei will decrease very quickly. So the curve will be steeper. If lower decay rate, so that means it will take a longer time for it to decrease by half. Okay, so by comparing the graph, you can see which one have a higher decay rate, which one have a lower decay rate. So generally, so if the half-life is shorter, then you see this one is shorter half-life. Okay, that means it can decrease by half very quickly. Then the decay rate will be higher. See, okay, this one the half-life is very short. Then the decay rate, okay, the decay rate is higher. If the half-life is longer, okay, take longer time to decrease by half, then you can see that the decay rate is lower. Get the idea? Okay. Okay, so solving problem involving half-life. Let's look at some example. A sample of radioactive material stored in the laboratory has an initial activity of 480 per second. 480 per second, it means that in 1 second, 480 nucleus already decayed. Or it can also mean that every 1 second, 480 radioactive radiation is emitted together here. Okay, so if the half-life is 6 minutes, how much is this activity after 30 minutes? Okay, so the information here, half-life is 6 minutes. So how much is the activity after 30 minutes? So the activity also can be calculated by using the same equation. N equal half power by n times the original number. So by using this equation, this is the activity. This is activity after n half-life. Okay, so this is original activity or initial, okay, original of initial activity. Okay, so this is number of half-life. Number of half-life already passed. Okay, so n equals half n times n naught. Okay, so how much is activity after 30 minutes? Okay, first what we need to do is we need to find, okay, because the half-life is 6 minutes, then we need to know in 30 minutes how many half-life already passed. How many half-life already passed? So very easy. Number of half-life that already passed will be equal to 30 minutes divided by 6. And then we get 5. That means 5 half-life already passed in 6 minutes. In 30 minutes, got 6 half-life already passed. So half power by 5 times 480. So you get 15, right? 15 per second. So that means after 5 half-life, the activity of 480 per second will decrease until left 15 per second. Okay, so this is one method of answering this question. That means you use the equation. This is one method lah. If you, for example, you don't know how to use this method, you don't know how to use this equation, or you forgot the equation. Okay, so what you can do is you can also answer this question manually. That means first you find out how many half-life already passed, and then you divide it by 2 manually. So that means at first is 480, and then after 1 half-life, you divide by 2. Okay, you take 480, you divide by 2, get 240. And then after another half-life, this 240 you divide by 2 again, so you get 120. After another half-life, it becomes 60. After another half-life, it becomes 30. After another half-life, Times 15. So see, you count that it's 30 minutes, 5 half-life already passed. So 1 half-life, 2 half-life, okay, 1 half-life, 2 half-life, 3 half-life, 4 half-life, 5 half-life. So after 5 half-life, 480 per second will change into 15 per second. So you can say activity. Answer again, activity after 30 minutes equal 15 per second. So this is the complete answer. So you see, usually this type of question is either 2 marks or 3 marks. So for example, 3 marks, in 3 marks, so that means to calculate the number of half-life, you get 1 mark. You can substitute correctly in the equation, you get 1 mark. And then the final answer, you get another 1 mark. If the question is 3 marks. Understand? Okay? If the question is 2 marks, then this one, calculate the number of half-life, no marks. Either this one no mark or substitute correctly no marks, but usually is this one no marks. Substitute correctly for marks. Okay, final answer for marks. But if like this, if you do like this manually, then how to get the marks for the working? This is the working. This is your working. So that means if the question is 3 marks, this show this, you get 2 marks. Understand? And then this one you get the mark number 3, the final answer. Get the idea. If the question has 2 marks only, so that means this thing that you show is 1 mark, and this one the final answer another mark. Okay, so that means if you want to do manually, you need to show this like this, 480 change to 240, draw arrow like this. This is the working. This is what I'm showing you here is the actual thing that you write as your answer. Okay, that you write as your answer. This is not like I show for fun. No, this is your actual way that you show your working. Okay, to get the marks. Okay, you must show like this. This number change to this number, okay, and you label 1 half-life. This number change to this number, okay, another half-life. This number change to this number, another half-life. So you can get the marks for working. Please do not just divide by 2, divide by 2, divide by 2 in your calculator, and then you just write the final answer. If you do that, you just press divide by 2, divide by 2, divide by 2 in the calculator, and you don't show, then you don't get the marks for your working. You only get marks for your final answer only. Okay, get the idea. Okay. Okay, continue. Let's look at the next example. Okay, a radioactive material stored in the laboratory has a half-life of 10 days. Okay, it says that the half-life is 10 days. Calculate the number of days taken for activity of the radioactive material to reduce to 25% of its initial activity. So we want to know how many days does it take to reduce to 25%. Okay, so first thing is we need to know how many half-life already passed. Okay, how many half-life already passed for it to reduce to 25%. So, okay, for this one, actually, it's easier if you do manually. Okay, so we want to know how many half-life already passed to reduce to 25%. So the beginning is 100%. After 1 half-life, reduce to 50%. After another half-life, reduced to 25%. So that means the number of half-life is 2. Okay, it's easier to do manually instead of doing with the equation. Because if you do with the equation, you have to use log and very tedious way of working. A bit complicated right? Okay, for example, if you want to use the equation is n equals half n 0. So this is what you want to find. How many half-life will it pass? So the final activity is 25%, half hour by n, and then the initial is 100%. So for 100%, after n half-life, reduce to 25. So you have to do calculation. Okay, so 25 over 100, so equals to half hour by n. So we continue here. So this is 1 over 4. Okay, 1 over 4 goes to half hour by n. So this will be 1 over 2 hour by 2 equals to 1 over 2 hour by n. So n equals. Okay, so you have to do like this, or you see this number is easier to see that is 1 over 4. But if this number is a number that is very big, okay, very weird number, then it will be very difficult to see it is actually half power by how much. Okay, half power by how many. Then you have to use what? You have to use log. Okay, you have to put log on the left side, log on the right side, and then calculate n is how much. Okay, you don't log right, logarithm, but you learn in your additional maths. Okay, so okay, so now that after we know the number of activity is, the number of half-life is 2, then we can calculate number of days for it to decrease to 25%. So one half-life is 10 days. So number of days taken, it will be equal to 2 times 10 days. So you get 20 days. Okay? So 20 days is the time taken for the activity of the sample of radioactive material to reduce to 25% of its initial activity. Okay? So next. Okay, so number 3, example number 3. The ratio of nuclei of argon-40 to potassium-40 in a sample of volcanic rock is 3 to 1. In the early formation of the rock, there are no argon elements trapped in it. If potassium-40 decay to argon-40 with half-life of 1,250 million years, estimate the age of the rock. Okay, so you see argon-40. This is potassium-40. Okay, the ratio is 3 to 1. Okay, so at first, at the beginning, there are no argon elements. At the beginning, argon is 0. Okay, and then potassium-40 will decay to become argon with the half-life of 1,250 million years. That means in 1,250 million years, half of potassium-40 will decay and turn into argon-40. Okay, get the idea. So, how do we estimate the age of the rock? First thing again, we need to find out how many half-life already passed. Okay, how many half-life already passed. So, for example, okay, so we can do like this. We draw a table like this. So at the beginning, argon is 0, potassium is 100%. Okay, 100% of potassium. So after one half-life, potassium will become 50% only, and then argon will have 50% also. Okay, because half of the potassium changed to argon, and then after another half-life, 50 become 25. So this one becomes 75. Okay, so you can see that because it says that the sample of volcanic rock, the ratio is 3 to 1. So that means you can see that this argon 40 is 75, this 25. So this ratio is 3 to 1. Can see or not? Okay, you can see that the ratio is already 3 to 1. So that means how many half-life already passed for the ratio of argon to potassium to become 3 to 1. So, 1 half-life, 2 half-life. Okay, let's see or not. After 2 half-life, the ratio between argon and potassium is 3 to 1. So that means number of half-life is 2. Okay, so the age of the, if one half-life is 1,250 million years, so age of rock will be equal to 2 times 1250 million years. So you will get 2,500 million years. Okay. So that means the age of the rock is 2,500 million years. Okay, get the idea. So this is how we estimate the age of the rock. All right. So until here, topic 6.1 finished. Okay, so we take a little bit of rest, and then we will continue with